We're going to spend the next couple of weeks looking extensively at motion, and one of the ways of representing the motion, in addition to the motion maps, would be with graphs. More specifically, position time graphs and velocity time graphs. We'll start with looking at our first type of graph will be the position time graph. A position time graph will show position on the y-axis, time on the x-axis. And instead of writing out position time every time, we can just call them xt. It's going to show an object's position at specific times. If you have a horizontal line on the position time graph, that means for those seconds the object is not moving. If you have a positive slope, it means we have a positive velocity. If you have a negative slope, it means you have a negative velocity. Since these lines are all straight, this is pretty straight, it means that the object is moving at a constant velocity. So, what that's telling us is between this point and this point, we're moving not at all, constant. Between here and here is a constant velocity, positive, and between here and here is a constant negative velocity. The slope of the position time graph tells you velocity. I can't emphasize that enough. If you have a steep slope, so our negative slope is steeper than the positive slope, it means it's going faster. The steeper the slope, the faster the object's going because the position is changing in a shorter amount of time. Here's how an example word problem would translate into a graph. A ball rolls to the right at 1 meter per second towards Kyle for 3 seconds. He stops the ball with his foot and holds it there for 2 seconds before giving it a kick to the left at 2 meters per second for 2 seconds. So our graph, we want to draw our axes, time in seconds, position in meters. We have a total of 3 plus 2 plus 2, so we have a total of 7 seconds. We want to make sure we give ourselves at least 7 hash marks. 1, 2, 3, 4, 5, 6, 7. And in terms of the y-axis, let's do the same. 1, 2, 3, 4, 5, 6, 7. And if we want to count by ones, we have 1 second, 2, 3, 4, 5, 6, 7. It's always important to label the axes, especially if the graph is quantitative, meaning numerical. So it tells us the ball rolls to the right at 1 meter per second towards Kyle for 3 seconds. Because it doesn't give us a position where the ball starts, we can assume that it's starting at the origin. So at 0 seconds it's at 0. At 1 second we're at 1. 2 seconds we're at 2. 3 seconds we're at 3. He stops the ball with his foot and holds it there for 2 seconds. So that means at 4 seconds it's still at 3 meters. For 5 seconds it's still at 3 meters. Before giving it a kick to the left at 2 meters per second for 2 seconds. So we go from 3 to 1. We go from 1 down to -1 at 7 seconds. So it's going to be somewhere around there. It is okay to go negative. And then we connect the dots. So this is what our position time graph would look like. Just extend this axis. Yes, you can go negative, so this would be -1. And that's what our graph would look like. The ball rolled with a constant velocity here. It was constant not moving here, and a constant negative velocity here. Our third segment right here is steeper. That's when it was going faster. Again, slope represents velocity, so steeper slope means faster velocity. We will be seeing a bunch more position time graphs, but let's look at a velocity time graph before doing a couple more examples. Our velocity time graphs we're going to draw a little bit differently. We're still going to put velocity on the y-axis, so meters per second. but we're going to have our x-axis intersect the y-axis, showing our time, because a lot of times we're going to have velocities that are both positive and negative. So positive will be above, negative will be below, 0 will be right in the middle. Any kind of horizontal line on a velocity time graph will mean constant velocity, and that's all we're going to see for the next few weeks, are constant horizontal lines on the velocity time graph. So say you're moving at a constant positive velocity, you're just going to have a straight line showing the velocity is not changing. If you come to a stop, and this is where these graphs are going to look a little bit different than anything you may have seen before, you can make this jump. So you're going to draw a vertical line down and say you come to a stop for a few seconds. You just want to shade in on the x-axis to show that your velocity is 0. Say you stop and now you're going to start at a higher positive velocity. The farther away from 0, the faster you're going. If you instantaneously turn around and start to go negative, you're just going to make a jump and then we would have a negative velocity. One thing to realize on the velocity time graphs is you will never, 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 never go backwards. Time can't go backwards, can't go negative. So your velocity time graphs will always, 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 always go to the right. Any kind of switch in direction is going to happen around here, where you go from being positive to being negative. And if you're stopping, again, it's not going to be absolutely instantaneous in real life, but these are ideal graphs. You're just going to use these straight little lines to show the jumps. If we look at our same example from the position time graph and we draw the velocity time graph for this, we want to show our axis with the velocity. We've got our x-axis with the time. We already know this has to go for a total of 7 seconds. And our velocities. It's rolling at 1 meter per second, and it's rolling at 2 meters per second. So let's just go 1, 2 on the top and the bottom. So to label our graph, this would be positive 1, positive 2, negative 1, negative 2, and 1, 2, 3, 4, 5, 6, 7. Our ball rolls to the right at 1 meter per second towards Kyle for 3 seconds. This means we have 1 meter per second for 3 seconds, a horizontal line showing that velocity is constant. He stops the ball and holds it there for 2 seconds, so it is not moving for those 2 seconds, before giving it a kick to the left at 2 meters per second for 2 seconds. Remember, left just means negative, so we're going down to the negative 2 meters per second for 2 seconds. So this would be the velocity time graph for the position time graph that we saw in the previous example. In the same example. Let's just look qualitatively at how the position time graph and the velocity time graph can be related to each other. In other words, once you have one, you can very easily get the next one. We'll start by looking at the position time graph and making it into a velocity time graph. I like to draw them one on top of the other. So for the position time graph, let's just say it has this general shape. We have a constant negative slope, we have a constant horizontal slope, and then we have a constant positive slope. For our velocity time graph, one thing that might be helpful is to draw dotted lines. So we've got 3 distinct segments on the position time graph, which means our velocity time graph will have those same 3 distinct segments. And we can just call them segment 1, 2, and 3. So for segment 1, our line is straight, our slope is negative, which means we're going to have a constant negative velocity. Segment 2, our line is straight and our line is 0, So we're going to have a constant 0 velocity. Segment 3, our line is straight, our line is positive, and it's not as steep as the first one. Not as steep means it's not moving as quickly. So we're going to go closer to 0 on our velocity time graph in the positive. One thing to remember, the closer you are to 0, the slower the object is going. So just because it's negative over here doesn't mean it's going slower, it just means it's going faster. Faster and to the left because it's below the x-axis. Let's now look at a velocity time graph and translate that into a position time graph. I'm still going to draw the position time graph and the velocity time graph underneath. Let's say this graph starts in the positive, goes to a shallower positive, goes negative, and then ends at 0. So here this graph has 4 distinct segments that we want to translate up to the position time graph. Let's make those lines look a little bit better. There we go. So for our position time graph, we're going to look at segment number 1. We've got a constant positive velocity. Compared to segment 2, which is also constant and positive, segment 1 is going to be a little bit faster. Doesn't matter where we start in the position time graph as long as our slopes are positive. So we're going to have a constant positive velocity. We're then going to have a constant positive velocity, just not as steep. Then we've got a constant negative velocity, followed by a constant 0 velocity. So, to show what this is, how they relate. Constant positive slope. Smaller constant positive, a shallower constant positive slope. Constant negative velocity, a constant negative slope. Constant 0 velocity, a constant 0 slope. If you feel okay with these graphs, then you are set for tomorrow. If you would like to see more examples, I will have another video with a few more examples, both qualitative and quantitative graphs.